Hello everyone, in this video tutorial we are going to simulate a process that involves momentum transport, heat transfer and mass transfer. So we have a parallel plate reactor. This is the top plate and this is the bottom plate. The bottom plate has a step down here. So the reactant is entering here, reactant A is entering here and it is converting into product B as it moves along the reactor. This is a heated cylinder. The temperature of the cylinder is 330 Kelvin and the inlet temperature is 300 Kelvin. So we are going to develop the velocity profile, the temperature profile and the concentration profile for reactant A. This is the 2D view of our geometry. This shows the heated cylinder and this is the top plate and this is the bottom plate which has a step. And this is the chemistry of the reaction where A is converted into product F. Sorry, earlier I mentioned it's B. It's not B, this is actually product F. And this is the rate of the reaction. First order reaction kinetics are followed. Rate is equal to Kca, where K is reaction constant. And the reaction constant can be estimated using the Arrhenius equation. This is the Arrhenius equation. A is the frequency factor, E is the activation energy, and this Rg, this is the gas constant. So we are going to simulate this process and we will develop velocity profile, temperature profile and concentration profile. So open COMSOL Multiphysics, click on file, then click on model widget and click on 2D. Here select the fluid flow and click on single phase flow, click on laminar flow and click on add. This laminar flow, this is actually, it is adding Navier-Stokes equation. So we need to add this for the velocity distribution. Now click on study and our process is a stationary process, that is a steady state process. So just select stationary and click on done. Okay, now click on parameters and from here you need to upload the parameters. You need to load the parameters. The link to that parameter file of that parameter is given in the description. So just click on load, click on parameters. So these parameters are loaded. You can find these parameters in the link which is given in the description. So you just download and then load files, load these parameters here. We go through these parameters. This is the geometrical parameter H1, the height, vector height W1 is this also denote the this is the reactor width and so on. This is the radius of the cylinder, the position of the cylinder where it lies inside the reactor. The inlet velocity, this is the diffusion coefficient, the activation energy, heat of reaction, this is the P vector or the frequency vector. Inlet concentration of the solute is 1000 mole per meter cube. Inlet concentration of the solvent. This is the MnA is the molecular weight of our reactant A, and this is the molecular weight of product B, product F. And this is the molecular weight of solvent, which is water. Inlet temperature, and this is the temperature of the cylinder. So now go to the geometry, right click on geometry and select rectangle. Here just write W1 and here write H1. Click on build selected. Now again click right on geometry, select rectangle and here write W2 and H2. Now again click on right. You can also do this from like if you click on geometry and here select circle. You can also add circle from here, right click on geometry and then circle. So circle, the radius is R1 and the position, the center position is X pose and Y pose. So we have built this geometry. Now click on in the geometry, click on Boolean information, click on difference and select this R1 and then activate this and select this cylinder C1 and this R2. Now click on build selected. So this is our required geometry. Now click on material, right click, add material from library and search water here, and double click on H2O water liquid. So water is added here to this domain. Now double click on laminar flow, right click on laminar flow. In the boundaries, add boundary inlet. So this is the inlet boundary. At the inlet we know the velocity, so this velocity is v underscore inlet. Okay, and also add another, click on right click, and then outlet. This is the outlet, and the pressure here is a 0. Okay, rest is wall 1, so everything else is wall. This is wall inlet and this is outlet. Now go to the mesh, and in the mesh select the element size, click on the extremely coarse mesh, click on build all. Now go to the study and click on compute. So this is the resultant velocity profile. You can see that the velocity is higher in this area as compared to here, because the fluid has a small area to flow through here as compared to here. You can also see that the velocity increases here. So if you want to see what is the velocity at any point, just click at any point here. This will give me what is the position xy and what is the value of the velocity. Okay, now you can also add the arrow plot. Just right click on this velocity, click on the arrow surface, and click on plot. So you can see the arrow surface here. You increase the size here, you can see that the size of the arrow increases as we move towards the center. That means that the velocity is actually increasing, and then we as move towards from the center to the upper wall, the velocity can decreasing. Okay, now let's develop the temperature profile. So for temperature profile, we need to go to the physics and click on add physics, and add the heat transfer. So click on heat transfer, and select the heat transfer in fluids, double click on it. So heat transfer in fluid is selected, and now if you see the equation here, if you just click on this equation, you can see that this is the equation which will be used for the analysis of heat transfer and for the development of temperature profile. You can see u here, which is the velocity. So this velocity, click on fluid 1, and then scroll to the velocity field user defined. So this velocity is already calculated by this laminar flow sphere. So that velocity will be used in this in the calculation of the temperature distribution. So this is actually coupling up the momentum transport with the heat transfer. So user defined, select you need to choose a velocity field actually. This velocity field which is calculated here, that will be used in the calculation in the analysis of heat transfer. Okay, and now we need to add the boundary conditions. So right click on heat transfer in the fluid and click on temperature. So select the inlet, the boundary condition 1, boundary 1, and now enter T underscore inlet. It's already given, right? And you can select boundaries from here, or you can select boundaries from here. Click on physics, boundaries, and click on temperature. So this temperature, this we also know temperature and this temperature of a cylinder. So just increase it the size and select the boundaries of the cylinder. And now this temperature is T underscore cell. Okay. And also add an outlet boundary, click on boundary and click on outflow. And this is the outflow, right? And now, so we have provided everything. Just go to the study and click on complete. Okay, still the velocity profile is shown. So just go to the results, click on 2D plot group, and call this temperature. Call this temperature. Oh, this let me this one. Call this temperature. Okay. Right click, click on surface, and just type T here, right? T. Click on plot. So this is the plot. This is the temperature plot. You can see that the inlet temperature is 300 degrees C, 300 degrees C, 300, 300, 300. The temperature is same until and unless it comes into contact with the cylinder. So now you can see the temperature is 321 here, temperature is 310 here, and so on. Okay, third is now we are going to develop the concentration profile. Okay, all I am doing, this is one way coupling. I am coupling mass momentum transport with the heat transfer, and now I am going to couple heat transfer and momentum transport with the mass transfer. So for that, go to the physics and click on add physics, and go to the chemical species transport, double click on transport of derivative species. Okay, and also add chemistry, and double click on chemistry. So chemistry is added here, and transport derivative species, this is also added here. Now you can see the equation here. So this is the equation that will be used. This is the equation that will be used for determination of concentration of ion. You can see that this term is for the diffusion, this term was for the convection, and this term is for the rate of reaction. So first in the chemistry, define the reaction. So click on chemistry, and in the phase select liquid, and right click on chemistry, click on reaction, and here write the formula A is equal to, and then this cap, and this sign, and then F. So click on apply. Now you can see that species A and F are added here. So click on this reaction, and reaction rate. This is a mass section rate now, and actually you need to define this okay, you click on use Arrhenius expression. So you need to enter the frequency factor A, and the E, the equation energy, right? And click on species A, and here the molecular mass of the species A is mn underscore A, which we have defined with this, and this is a molecular mass of F. This is mn underscore F. Okay, now again click on transport of derivative species, and in the dependent variable just write CA here. This is so this is actually the variable name, CA. Okay, now if you okay, now we need to add the reaction here, and now we need to add the reaction to the transport derivative species and the boundary condition. So just click on physics, and then click on domain, and click on the reactions, So reaction 1 and reaction 1 here user defined. So reaction rate was species A, which we have already defined. Okay, and just click on this domain. It is now added here. Now add the input and output condition. So click on inflow, and this is a C underscore inlet. Let me confirm that if this is C underscore inlet. Yeah, this is a CA underscore inlet, right? CA underscore inlet. Inflow is a CA underscore inlet. Huh? This is C underscore inlet, and this is the input. Also add the outflow. So this is outflow. Okay, now just run the simulation. Click on compute. Okay, now we need to display the concentration profile. So click on result, click on 2D plot group, and rename this with concentration. Okay, and right click on this concentration, then click on surface and just write CA here and click on plot. Oh, there is some problem because the concentration is not changing the way it should be changing. So yeah, exactly, there is a problem actually. We forgot something, and that is click on the transport properties one. So here this user defined, we have not coupled the velocity, the momentum transport with the mass transport. So this is mandatory. So you need to select velocity field. Now click on compute. Now we shall see a different concentration profile. Concentration. So this is the concentration profile, right? You can see that as the fluid moves, the concentration of the A decreases. Here you can see that the concentration is 800. Let me clear this. Concentration here is 922 mole per meter cube. This is the unit of, and here it drops to 412 mole per meter cube because it is reacting continuously. Okay, now we can also couple mass transfer with the heat transfer. Actually, as you know that this is an exothermic reaction, so there is heat of reaction. So as the reaction progress, the heat may be released, and we may expect high temperature in this region as well. So for that, just go to the transport of okay, first go to the chemistry, and in the chemistry you need to select the, so we go to the reaction, this reaction, and enthalpy of reaction. So here I'll go to the enthalpy of reaction, enthalpy of reaction, enthalpy of reaction. Change this from automatic to user defined, and write H here. This is the enthalpy of reaction we have, which we have already defined in this has been already defined in the parameters. So enthalpy of the reaction, you need to define this and then go to the heat transfer. Right click on heat transfer and click on heat source. In the heat source, add the heat source to this domain, and general heat source user defined. No, this is heat source of a reaction. Okay, now run the simulation. Okay, before you run the simulation, it is advised to do the multiphysics coupling. So just go to the multiphysics, right click, and non-isothermal flow, and also this reacting flow dilute species. So now click on compute. Now we are doing two ways coupling. The momentum transport is coupled with the heat transfer. Heat transfer is coupled with the mass transfer, and mass transfer is also coupled with the heat transfer. It means that heat transfer affects mass transfer, and mass transfer will affect the heat transfer. So this is called two-way coupling. Now if you just click on the temperature and surface one, you can see this figure. Earlier you saw the temperature was not changing until the fluid reached to this cylinder. Now you can see the temperature here is 308 Kelvin. So earlier it was 300 up to this point, and now the temperature rises before even if it touches the cylinder, and the reason is that because we have exothermic friction. Thank you for watching. Please like this video and share with your colleagues and friends. Thank you very much.